Now this is called an end-path filter, and it's a bit of electronics that I learned about fairly recently that, despite having a fairly basic functionality, is actually pretty interesting. Interesting enough to me to make a video about, which you're watching right now. So first of all, let's take a look at what an end-path filter actually does in the first place. So right here you can see we've got the filter itself, surrounded by a bunch of equipment that allows me to demonstrate its functionality. So first of all, we've got my phone over here acting as a signal generator. So right now this is generating a 4000 Hertz audio signal, which then goes into an audio amplifier over here, and from there it goes into the end-path filter. And then the output of the end-path filter is connected to my oscilloscope so that we can see what comes out of it. Now, before we take a look at the output signal, let's just take our scope probe and wire it up to the input so we can see what's actually going into the filter at the moment. And I've pointed another camera at the oscilloscope screen so you can also see this. So as you can see, the signal going into the filter at the moment is just a 4000 Hertz sine wave with an amplitude of around 0.6 volts or so. So now let's take a look at the signal that comes out of the filter. Let's plug our scope into this side. There you go. And essentially it's an uglier version of the input signal, right? It's sort of a stepped, squarish version of the input waveform, and its amplitude is a little bit lower too, and we'll talk about that later on in the video. So now let's see what happens if we change the frequency of our input signal. So let's just go over to my phone, and we're going to set it to, I don't know, let's say 3500, so 3.5 kilohertz. There you go. And so now we've barely got anything left on the scope, right? It's pretty much entirely blocked by the filter. And this is even worse if I go to, let's say, 3000. And it also happens if I use higher frequency, so let's say 4.5 kilohertz instead. Same thing happens, 5000. So anything that's not close to 4000 Hertz is getting blocked by this filter. And it's rather selective as well, because if I set it to, let's say, 4050, so that's 4.05 kilohertz, you can see that is already significantly lower than if I set it to, let's say, 4000 or 3994, which is what I set it to in the beginning. That's pretty much the optimal value right now. So it's a rather selective band-pass filter, right? That's what it is. Not very spectacular, I have to admit. But the cool thing about this filter is how it's programmable. So as you can see, there is an Arduino wired up to the filter, and that Arduino is then wired up to my laptop. And so what I can actually do is I can tell this Arduino to reconfigure this filter to allow different frequencies to pass through. So let's say I want the filter to respond to 3000 Hertz instead. What I can do is I can simply type in 3000 and then send it to the Arduino like this, and on the scope you can immediately see our signal pretty much disappearing, which means the filter is now different. And then if I change the frequency to 3000, it should come right back. There you go. So it is a customizable, reprogrammable filter. Now, I know what some of you are thinking about this. Some of you might be thinking, well, hang on, there is a microprocessor sitting here, and there is a stepped output waveform being generated. This is just some kind of digital filter, right? It's digital processing. The Arduino is just processing the signal in some way, and then outputting it again. But that's not actually what's going on here. The Arduino is purely used to control the filter. The Arduino never actually gets to see the signal that comes in. So it is an analog filter, but it can be controlled by a microprocessor or a microcontroller of some kind. So now, without further ado, let's take a look at how this thing actually works. Now, the design of the N-path filter that we just looked at is based on a very simple electronic filter that you might actually be familiar with. It's the RC low-pass filter, which looks like this. And that's just a resistor followed by a capacitor. And the way this filter works, of course, is that to very, very low frequencies, the capacitor appears like an open circuit, and so the signal is barely affected by it and can simply pass right from the input to the output. Whereas to very high frequency signals, the capacitor will appear more like a low impedance connection to ground, or even a short circuit to ground, and so the output signal is going to be very, very small, and therefore the signal will get blocked. And so that is how this filter is able to let low frequency signals pass through while blocking higher frequency components, which can be extremely useful if, for example, you have a signal with a bunch of high frequency noise on it that you need to get cleaned up. And of course, you can tune or select the cutoff frequency of this filter, which is sort of the frequency above which it starts blocking things, by picking the right value for your resistor and capacitor. Now, the N-path filter that we just looked at, though, does something different. Because it's not a low-pass filter, it's a band-pass filter. So if the frequency is too high, it'll get blocked. But also if the frequency is too low, it'll get blocked. So how does this simple circuit change to become a band-pass filter? Well, let's take a look at a little diagram that I've made. So right here you can see a super wacky circuit that consists of a resistor and multiple capacitors. But there is a twist, or maybe a turn, I don't know exactly what to call it, because these capacitors are not fixed. These capacitors are mounted on a wheel that can spin, like this. And one capacitor at a time will touch this ground symbol over here. So one capacitor at a time, depending on the position of the wheel, is actually connected to ground. So one capacitor at a time is part of the circuit, while the other ones are just sort of dangling there doing nothing. So now let's say that we're going to be spinning this wheel, and at the same time a signal comes into the input of the filter. And let's say that this signal has a frequency that matches the speed of the wheel. So that means one period of the signal is the same amount of time as it takes for this wheel to complete one full rotation. So this happens to be perfectly synchronized to the speed at which this wheel is spinning round, okay? Just in this case. So what does that mean? Well, it means that each capacitor on this wheel is going to see the same part of that signal every time it comes round, right? So let me just grab a little marker so I can draw it. This capacitor here, for example, will always see this part of a signal. And this capacitor over here, actually the wheel is spinning this way, right? So it's this one's the next one in line. This capacitor is going to see maybe this part of the signal. And then this capacitor is going to see maybe this part of the signal, and so on and so forth. And every time the wheel comes around, those capacitors are going to see the same chunk of the signal because the period time of the signal matches the speed of the wheel. So, as this goes on for a while, those capacitors get charged. And because every time they get connected, they see the same effective voltage. So this capacitor is going to get charged to the average level that it sees, which is, right around this. And the next capacitor is going to charge to right around this level here. And the next one is going to get charged maybe to, I don't know, this level. And that way it just keeps going, and these capacitors get charged over time. And that way you get this output waveform, which is sort of a stepped version of the original signal, which is what we just saw in my little test setup. But what happens if the input signal has a different frequency than the speed of the wheel? So the speed of the wheel is no longer synchronized to the frequency of the input signal. So let's say the input signal has a slightly lower frequency now. So that means, let's say the signal comes in, right, and at some point the wheel is already done making a full rotation. So let's say at this point in time the wheel has already completed a full circle. So that means in the beginning this capacitor might see this part of a signal, But then, once it comes round the next time, all of a sudden it sees this part of a signal, which is different. And the next time it comes around, it's going to be something else again, because once again, the speed of that wheel is faster than the frequency of a signal. So let's say a new rotation of the wheel will start here, and it'll be done the next period maybe like here or something. And so then the capacitor sees this, which, oh, okay, that happens to be about the same level, but the next rotation, it might be here. And so that's not just true for this capacitor, that's going to be true for all those capacitors. Because the wheel is no longer synchronized to the frequency of the input signal, every time a capacitor gets connected to ground, it's going to see a different part of that signal. It's going to see some other voltage. One time it might be this, then it might be that, then it goes that again, and it just jumps all over the place. And so those capacitors will not really get a chance to get charged up. Okay, so in the beginning, when we had the frequency of the input signal matched to the speed of the wheel, every time a capacitor is connected, it always sees the same part of the signal. And so eventually the capacitor has a chance to get charged up to that level. But in this case, now that our input signal has a different frequency, each capacitor is going to see a different chunk of the signal, and therefore a different voltage every time it's connected, and it's not going to get a chance to get charged. And so the voltages in those capacitors will stay very, very small, very close to zero, and therefore your output signal will be very close to zero. And by the way, of course, that also applies if the frequency of the input signal is greater than the speed of the wheel. And so that way you get a frequency response that looks kind of like this. And this is actually a plot that I made based on the filter that we just looked at. You get a very good response for a particular frequency, and as the frequency goes up or down from that, the response goes down quite dramatically. Now, one thing that you do have to keep in mind about this is that there is also going to be a response for multiples of the center frequency. So if the frequency of the input signal is exactly 2 times or 3 times or 4 times as high as the speed of the wheel, that will of course also give you a response. So if you plot this chart for a bigger range of frequencies, you'll find more spikes for multiples of the center frequency, and that might be something you have to take care of in one way or another. Now, of course, in reality, you're not going to be doing this with a physical spinning wheel, because even in our example, where I used a frequency of only 4 kilohertz, which in electronics terms is a super low frequency, because you might want to do this at 1 megahertz or 100 megahertz or a gigahertz, right? So 4 kilohertz is really nothing. But even at 4 kilohertz, if you wanted to do that with a spinning wheel, I think that's 4,000 hertz, or 4,000 revolutions per second. So 4,000 times 60 would be 240,000 RPM, is that correct? Crazy high RPM, and even, that's for a low frequency. Imagine you want to do this for 1 megahertz or 100 megahertz, how fast your wheel would have to be spinning. It would be insane. It would be a hazard to stand next to if that was on the table. So instead of doing this with a spinning wheel, of course you're going to be doing this with switching devices. So you're going to have an array of capacitors which you can connect into the circuit using switches, which are probably just going to be transistors or MOSFETs that you can switch on and off. And then you can use a microprocessor of some kind to provide a clock signal to activate those switches at the right time and effectively create this situation in a solid state way. So if you look at this circuit, you can see that it resembles pretty much exactly what we just talked about. So you've got, first of all, on the input, you've got a little resistor right here, which I think is a 2.2 or a 4.7K. I can't quite remember what I used. I built this last week. And then you've got 5 capacitors, 1 microfarad capacitors, which are hooked up to the main sort of output of the filter. And then all of those capacitors can be connected to ground using MOSFETs. There is 1 MOSFET for each capacitor, and those MOSFETs are being driven by the Arduino. And so the Arduino is simply sending pulses to those MOSFETs, turning them on and off in a sequence, to produce our effective sort of spinning wheel effect that we talked about. And so, for example, if I want the filter to respond to 4000 Hz, I send the number 4000 to the Arduino. The Arduino will then calculate that that means that each switch or each MOSFET needs to be turned on for 50 microseconds, and so it'll make 50 microsecond pulses, meaning your period time will be 250 microseconds in total, which of course corresponds to a frequency of 4000 Hz. Now, you might also notice there is an additional capacitor on the output sitting right here, which is always connected to ground. Basically, I added this to remove a bit of noise. If you don't have this capacitor, it still works, but you get some spikes, some voltage spikes, presumably because of the switching going on. So I just added that in there to clean up the signal a little bit and get a more clean waveform on the scope. Now, something that's interesting about the filter that I demonstrated was that the amplitude of the output signal was significantly lower than the amplitude of the input signal, even when we were exactly at the right frequency. So why was that? Why was that attenuation there? Well, I have a theory about this. I'm not entirely sure if it's true. I think I'm 80% sure it's true. But my guess is that this is because of the body diodes in my MOSFETs. So as you might know, if you have an N-channel MOSFET, which is what I'm using here, there is effectively a diode in there going from source to drain, which allows the MOSFET to conduct current in the reverse direction, even if it's switched off. And so I suspect that in this case, that might be allowing my capacitors to charge or discharge when they're not really supposed to, at least a little bit. The reason I think this is because the gain of the filter appears to increase as I lower the input voltage or the input amplitude, which would be explained this way because, of course, the current conduction of a diode depends on the voltage across it. So if you make that voltage lower, your sort of leakage current should go down. So that is just my theory about this. Let me know in the comments if you have a better idea. So this type of filter is kind of neat because you can make a programmable filter, an adjustable filter that you can configure to operate over a wide range of frequencies by simply adjusting a clock signal that drives those switching devices. You don't need any adjustable components or like mechanical things to get it to work. You only need a resistor, a bunch of capacitors, and a bunch of switching devices like transistors, which also means this type of filter is very suitable for making an on-chip designs. So if you need to make a microscopically small filter that goes inside of a processor, like let's say a processor that you want to use inside of a phone or something, this is an excellent choice. So anyway, that's it. That's the end-path filter. As I said, I only learned about it fairly recently, but I thought it was so cool that it deserved a video, so hopefully you thought it was interesting too. If you enjoyed this video, maybe consider clicking the like button or subscribing to this channel, and of course, thank you very much for watching.